In this quick tip, let's talk about matrices. Let's talk about why they're important, what you can do with them, and I'll also relate this back to our last quick tip about quaternions. So, matrices, what are they? Well, it's really just a way of collecting data. It's a table of numbers, and these numbers can be used in some kind of way to alter our 3D scene. So, here we have rows and columns, as you can see, and as I just said, it's really just a collection of data that looks like this. It's a way of organizing data, and most often, as 3D artists, this will relate to some kind of task involving your points moving around. Now, a matrix doesn't have to be about moving your points around in 3D space, but as 3D artists, this is what we use matrices for the vast majority of times. So you might also hear terms like a rotational matrix or a translation matrix or an identity matrix, and that might kind of seem confusing at first because you might think that there's something intrinsically different about these special matrices that make them rotational or translation or whatever. But just keep in mind that a matrix is still just a collection of numbers. The only difference between these terms when people talk about this stuff is how you apply the data to whatever's going on. So a rotational matrix is a matrix that gets built and is being used to rotate something. A translation matrix is the same kind of thing, except it's a matrix that's been made to then translate your points in space. So, as an example, let's say that we want to rotate some points. This is a 3x3 rotational matrix. And don't mind this cosine and this whole sine, negative sign thing for right now. Just keep in mind that if we multiply this rotational matrix against our position, we will end up with a new rotated position on our points. If we want to translate something, we can use a 4x4 translation matrix. Again, multiply it times our position, and now we've translated our points to a different location. Now you'll also notice that whenever you make a matrix, we are making these in squares. So you won't have a 3x4, you won't have a 2x3. This always is 3x3 or 4x4 or whatever. And so just keep that in the back of your mind. And also I'll go over the details on how you can understand these numbers here in a minute. But just for now, know the effects. Also, we have this identity matrix. And an identity matrix is basically just a matrix, which looks like this. And whenever you multiply it times your position, there's no change in position. So it's kind of like multiplying your position times 1. It just stays the same. So now let's go into Vex, and I'll show you why an identity matrix is cool and how we can actually take this and rotate something. So here we have this hammer, and I like to rotate the hammer and Y like this. But now I like to do this through Vex and through applying some kind of rotational matrix against the hammer. So let's start off by making a 3x3 matrix. We could just say matrix 3, and that'll create the 3x3. And let's call this our rot Y. And set this equal to a function called ident. Not indent, but ident. There we go. And as you might be able to imagine, ident creates an identity matrix. And an identity matrix, again, when you multiply it against a position, just keeps everything the same. So let's just prove to ourselves that that's the case by taking our position and multiplying that against rot Y. Again, nothing's changed. And you might be wondering, well, okay, why do we do that? Well, now we have something to work on. We've kind of generated this matrix, and now we can do something to that matrix with other functions. In this case, the function I'm going to use is rotate. Let's highlight that, press F1, check out the ingredients we need. I'm going to use the second version right here, where we specify rotation Y, that's our matrix. We'll have some kind of amounts. So let's create our own channel for this. So channel floats. We'll say rotation Y underscore amounts, like that. And then, oh, I got two M's there. There we go, amount. And then finally the axis. So we're going in Y, so let's create a vector information which says 0, 1, 0. Okay, create the parameter right there, and now we can rotate. Pretty cool. And if you watch my last quick tip, you'll also know that this is now rotating in radians, not degrees. So to change that, we can just say radians, capture our rotation amounts in there, and now we can rotate this in degrees. Now, if you're like me, I like to visualize things as much as possible. So here's a cool way of doing that with a rotation matrix. Think of it like this. You are basically drawing out the XYZ handles. So if you think of this as a vector, which describes where something is going, or a location in space relative to a point, this is XYZ. Also, if you were to, let's say, take this number, and let's say we took our Z and turn it into 2, you would essentially be scaling something in the Z direction. So that's kind of how scale works. With rotation, it kind of looks like this. So let's say we want to rotate something along the y-axis. These are just vectors. They point in some kind of direction, and all we would need to do to rotate something is change the way, or change the direction in which these handles are facing. So we're basically just redrawing our handles maybe out here and out here, and we can represent that change through different values in the X and Z axis, and that is how rotation basically happens. Okay, so that's how you visualize it. Where I'm going with this is that, let's say at some point or another, Thor just, throws a hammer through the air, and you want the hammer to rotate going like this. Eventually, we're going to take an axis and replace it with something else, like velocity, where this hammer is going. And once you are in that whole situation, now you have the background knowledge to know what this is trying to describe, and you'll know what to do now, because if, let's say, we substitute velocity here in V with our, let's go Z. You're supposed to do it in Z. Let's say we went Z with that. Now we know that we can define a y-axis and a Z, or y and x-axis, and that will be everything we need to apply a matrix and rotate the hammer like so. So anyway, that's just kind of where I'm going with this. If you haven't yet, watch the last quick tip. That's kind of where I introduced this whole idea of using Vex to rotate something like this. Something that's also interesting is that at this point, you've now seen two ways of rotating something, with quaternions and with the rotational matrix right here. So in the next quick tip, I will be talking about how to combine those two worlds, what the deal is with quaternions. I still haven't really told you exactly what they're all about, and it's going to be really cool. So thanks again for watching, and until then, have a great day.